Okay, I think why don't we go ahead and get started. I'm very happy to welcome Ioannis Panageas. So Ioannis did his undergraduate work at the National Technical University of Athens, and then his graduate studies at Georgia Tech, where he had got a master's degree in mathematics and was involved in their algorithms, combinatorics, and optimization program for his PhD. And then following that, he did some work at MIT as a postdoc. And as he'd been working on a variety of theoretical problems, and in his postdoc, really started to look more at some problems that have big implications for modern machine learning. So Ioannis is currently in Singapore physically. So he was on the faculty at the Singapore University of Technology and Design. Happily, he's joining us here at UCI. We haven't been able to welcome him in person yet, but I'm eager to hear about some of the work he's been doing on properties of the first order methods that are widely used in machine learning. So Ioannis, please go ahead.
Hi, everyone. So today I'm going to talk about some works that I did the last, let's say, 2-3 years. Basically, the title is First Order Methods Almost Always Avoid Saddle Points. But I added also a second title that says An Asymptotic Point of View, because all the methods that we are going to analyze, we will see the convergence properties in the limit. So all the works for this talk do not have rates of convergence. They have only asymptotic behaviors. This is joint work with a lot of people, Jason Lee, Yorgos Pilouras, Maximovich, Skoulakis, Adonis Varvitsiotis, Ben Recht, Xiao Wong, and Michael Jordan. So my talk will be more intuitive, less technical, and I hope you enjoy. So let me start. So what most people do in machine learning, they care about optimization. Let's say you have a function for the case of this talk in C2, meaning twice differentiable and the second derivative is continuous. And suppose that you want to minimize this function in the whole Rn. This means you don't have any constraints. So if you want to find the global minimum of this function, this problem is very challenging, is NP hard. Okay, so a solution concept that typically people are using in machine learning is the local minima. You might ask why local minima? Well, they are robust solution concepts, and basically it is the best you can hope for, since reaching a global minimum is is NP hard. And the methods that have been used for training neural networks, etc., are first order methods. So these are methods that essentially have access to the values of the function and the values of the first derivatives of the function. These methods are easy to implement and fast to implement, so people like them. Maybe the most well-known algorithm, first order method, is gradient descent, which is basically defined like this. So the next iterate is equal to the current iterate minus some step size times the gradient of your function at the current iterate. So this step size, if you see, it has a subscript k, which means that it might depend on the iteration. So if it does not depend on the iteration, we call it constant step size. it's very crucial how to choose the step size. It shouldn't be too small as a function of k. For example, if it is, let's say, 0, the step size, then your method doesn't do anything. Okay, it gets stuck at every point. So it shouldn't be too small, it shouldn't be too large. So we will see later what should be the choice. And then there are many other methods that are used. Some examples are mirror descent, coordinate descent, proximal point, and so on and so forth. So let me just note that, this method, gradient descent or mirror descent, or any method you want, your favorite first order method, can be seen as a discrete time dynamical system. So basically, a dynamical system is of this form. G is called the update rule of the dynamical system. These are discrete time, okay? There are also continuous time, which are essentially ODEs. And when your step size is constant, you can say that the dynamical system is time homogeneous. But if it is not constant and changes with the number of iterations, then the update rule depends on the current iterate, but also depends on the time. So you can have either time homogeneous or time non-homogeneous. And why I'm saying this? Because later on we will see some fundamental properties of dynamical systems, and these techniques essentially will be used to understand the asymptotic behavior of first order methods like gradient descent for this particular talk. So you might ask, okay, gradient descent, people are using it. Are there any provable guarantees? Well, there are some guarantees. One typical assumption for your function f is that the gradient of f is Lipschitz. These functions are called, if it is L Lipschitz, are called L smooth. So one can show that if your function s f is differentiable and L smooth, then essentially if you run gradient descent, the value at the current iterate minus the value at the next iterate is essentially a positive number, a non-negative number, which means that the value of your function essentially decreases along the trajectories of gradient descent. So when you apply gradient descent, you observe that the value of your function always decreases on the trajectory. So this implies that you will have some sort of convergence, okay? So it's not hard to show. It's a typical course. If your function is convex, then after t iterations, where t is of order the Lipschitz constant over epsilon, you will get close to an epsilon minimum, where epsilon minimum essentially means that the value of your function is at most epsilon far from the optimal value. Okay, so when your function f is convex, you have basically you have every local minimum is global because you have uniqueness, and in this case you are guaranteed to get a minimum. And whenever you have, let's say, something that's called strong convexity, you can have much faster rates. Basically, you can be logarithmic to 1 over epsilon. But when your function is not convex, you might have some sort of convergence, but then you might converge to something that's called the saddle point, which is a bad solution for us. Okay, as I told you before, that we care about robustness. So a good solution concept should be the local minima. So here is an example of a non-convex function. You can see that there are many, let's say, local maxima, local minima, and a lot of saddle points. Are there any questions so far? Okay. So as I told you, you can see the gradient descent and all other first order methods I mentioned as dynamical systems. Okay. So let me give you some 2-3 slides introduction for linear dynamical systems, just to get some intuition. And this is more like basic linear algebra. Okay, so what is a linear dynamical system? A linear dynamical system given a matrix A and of size n times n, let's say symmetric. Okay, a linear dynamical system is of this form. So the next iterate is equal to A times the current iterate. Okay, so it's easy to see that by, let's say, telescopic product, that the T iterate is essentially the matrix A raised to the power T times the initialization. So one question is that, 0 is a fixed point of this dynamical system. What is a fixed point? Basically, it's a point that is invariant under the update rule of the dynamics, which means that if you start from 0 and you apply this update rule, you will still be at 0. So, and then the question, the first question you might ask is that when this linear dynamical system converges to 0. So the answer is quite simple. As you can imagine, it depends on the eigenvalues of the matrix A. Okay. So here is an interesting lemma, which is trivial to show. When you have a symmetric matrix that has a spectral norm less than 1, then no matter what is the initial condition, you always converge to 0. Okay. So the proof is just trivial. You take the initialization, you write it as a linear combination of the eigenvectors of the matrix A, because it's symmetric. It has real eigenvalues, and the eigenvectors span the whole space. And then you write the T iteration like this. Okay. So since all the eigenvalues are less than 1, basically every term of the summation goes to 0. Okay. So it turns out that as t goes to infinity, no matter where you start from, you converge to 0. So, and the same can be shown if A is not symmetric. So if A is not symmetric, then you can show using Jordan decomposition that not when the spectral norm is less than 1, but you can do even better when the spectral radius is less than 1, which means the eigenvalue, okay, not the singular value. So now the question is, okay, cool. When all the eigenvalues are less than 1 in absolute value, this means that when no matter where you start from, you converge always to 0. But what happens if you have eigenvalues that are greater than 1 as well? So you have like some eigenvalues that are greater than 1 in absolute value, and some are less than 1 in absolute value. And then the answer is we don't know if it converges to 0. It depends on the initialization. Okay. So in particular, what you can show is that you will converge to 0 if and only if the initialization belongs to the span of the eigenvectors with eigenvalues less than 1 in absolute value. So as long as x0 doesn't have a component, doesn't have an eigenvector with eigenvalue greater than 1 in its span, then you converge to 0. If this is not true, then you can show divergence. Basically, you can show that the norm goes to infinity. Okay. So this stuff might sound to you very trivial, but this is the intuition to go beyond and to understand the behavior of gradient descent. So before I explain the main theorem that says, gradient descent essentially avoids what we call saddle points, let's do also a warm-up on quadratic functions. So a quadratic function is a function of the form x transpose ax. Again, A is a square matrix, symmetric, okay? So let me tell you that we may assume that A is symmetric because if you take any quadratic function where the matrix A is not symmetric, you can essentially symmetrize it with this trick, okay? So you may assume that the quadratic function you have, the matrix is symmetric. So now, if you run gradient descent for this particular function, it turns out that the next iterate is identity minus step size times the matrix A times the current iterate. And so this is the closed form, essentially, solution of the update rule of gradient descent. So you observe, basically, that this is nothing but a linear dynamical system. So whatever I just mentioned for linear dynamical systems, we will apply it to quadratic functions, basically. So here is an interesting lemma. Suppose that you have a symmetric matrix of size n times n. L is the maximum eigenvalue of A in absolute value. If we set the step size to be 1 over L, then if 0 is a local minimum, then gradient descent converges to that minimum for all initializations. Okay. So no matter where you start from, if you choose the step size to be less than 1 over L, where L is the maximum eigenvalue of A in absolute value, then you are guaranteed to converge. And this is sort of tight, so you can construct examples where if the step size is greater than this, you might not have convergence. So the proof is trivial, basically. What you can say is that if 0 is a local minimum, it means that the matrix A is positive definite, okay? So basically, you can show that if you choose alpha, the step size, to be less than 1 over L, you can show that the step size times the matrix has all its eigenvalues in the interval 0, 1. And then the identity minus this matrix has also its eigenvalues at 0, 1. So all the eigenvalues of the matrix identity minus step size times symmetric A, they have all its eigenvalues between 0 and 1. So using the previous statement, you can guarantee that the limit goes to 0 no matter what is the initialization. And then the question is, what happens when A has negative eigenvalues? Well, that's when essentially you have a saddle point. So in this case, when you have also negative eigenvalue, 0 is not a local minimum anymore, it is a saddle point. So, and suppose you have a saddle point, okay? Under what assumptions do we converge to it? Basically, we use the previous, again, machinery. You converge to it as long as the initialization lies in the span of the eigenvectors of this matrix identity minus alpha times A in the span of these eigenvectors with corresponding eigenvalues less than 1. So, and let me give you some notation which we will see later. So suppose ES is the span of all the eigenvectors that have eigenvalues less than 1, and EU, so S stands for stable and U for unstable, is the linear space that is the span of the eigenvectors that correspond to eigenvalues with absolute value greater than 1. So what is the conclusion for the quadratic functions? You converge to 0 if it is a local minimum, and if it is a saddle point, okay, you will converge to it if and only if the initialization lies in the EES, in the, let's call this the stable linear subspace, okay? Now, here is to get some intuition, how likely it is that the initialization lies in this linear subspace, okay? So let me tell you that this linear subspace has dimension k. So k eigenvectors, dimension k, and the unstable one has n minus k. So whenever k is less than n, it means that this linear subspace is lower dimensional, is of dimension k, which is less than n. So if you start, let's say, at random from your whole space Rn, what is the probability that the initialization lies in the low dimensional subspace? Well, the probability is 0, basically. So it's very unlikely that the initialization starts from this stable linear subspace. And formally, what you can say is that if you choose the step size to be at most 1 over L, where L is the maximum eigenvalue of this matrix, A, for the quadratic function, take any continuous distribution in Rn, take and get a sample, an initialization from that distribution. The probability to converge to a saddle point, to the saddle point 0, the probability is 0. Okay, as long as, you know, if it is a saddle point, it means that this stable set is lower dimensional, has dimension k, which is less than n. So any questions so far? Okay, so let's move forward now. I will explain. So you got some intuition, yes? Okay, so you got some intuition about linear dynamical systems. We applied this intuition to understand the gradient descent, the asymptotic behavior of gradient descent on quadratic functions. So more or less everything was trivial. And now let's move forward to general non-convex functions. Okay, so let me provide you some definitions before we proceed. So what is a critical point? A critical point is a point xr where the gradient of f is 0. We call a point saddle where if it is a critical point, but it's not a local minimum. Okay, and we call a critical point strict saddle as long as the minimum eigenvalue of the Hessian is negative. So basically, first of all, the Hessian is a symmetric matrix, so all the eigenvalues are real. Now, assume that there exists an eigenvalue that is negative, okay? So saddle points are guaranteed to have eigenvalues that are non-positive, okay? So strict saddle is when there exists one eigenvalue that is strict less than 0. So in the previous case, if A had negative eigenvalues, x0 was a strict saddle point, okay, for the quadratic case. So the main theorem basically of this talk is the following. So suppose that you have a function that is C2, and suppose that the gradient of that function is L Lipschitz, okay? And assume that, 0 is a critical point of this function and is also a strict saddle, meaning that the Hessian of your function computed at 0 has an eigenvalue that is less than 0, is negative. And choose your step size alpha to be 1 over L, constant, but strictly less than 1 over L. Now, for any continuous distribution, D, in Rn, okay, if you take an initialization sample from that distribution, the probability that the gradient descent converges to critical point, to the strict saddle point 0, that probability is 0. So basically what we saw for quadratic functions, you can show it for any twice differentiable function that the gradient is L Lipschitz. So how do we show such a thing? Well, first, you write down the, let's say, the update rule of gradient descent, and what the idea is basically to linearize your system, okay? So whenever you linearize your system, you have like basically a linear dynamical system where the matrix here is nothing but identity minus step size times the Hessian at the critical point. And then you have some error, okay? Now, if you are very, very close to the critical point, this error is negligible, okay? So if you are very, very close to the critical point, you think that your system, the first order approximation, basically the linearization approximates the system really well. So if this is true, then why don't we use the machinery we had for quadratic functions, basically, for linear dynamical systems? So basically, this is what we are going to do. But to do that, we need to use basically a very, very fundamental and very important theorem from dynamical systems. This might be a bit scary, this particular slide, but I will try to decipher every sentence. So this fundamental theorem is called Stable Manifold Theorem. Okay, so suppose that you have a dynamical system of the form xt plus 1 equals phi of xt, and you are interested at 0 and say that 0 is a fixed point. So this means that phi of 0 is equal to 0. Okay. So suppose that your function is, at least 2 times differentiable and 2 times differentiable and has continuous derivatives. Moreover, suppose that your function is something that we call diffeomorphism. So diffeomorphism means basically that your function is differentiable, okay? But also it's an 1-1 mapping, and the inverse is also differentiable. So this is if you haven't seen it before, it might take some time to digest, but let me tell you that basically gradient descent satisfies all these properties. Okay, so suppose that you have such a dynamical system, then what you can do is that you can take the Jacobian of the dynamic of the function phi of the update rule, compute it at 0. You take the Jacobian. Now you compute the eigenvalues of the Jacobian. So you have the eigenvalues that have absolute value less than 1, and you have the eigenvalues that have absolute value at least 1. Okay, so you can decompose your space, let's say Rn, to ES and EU ES stands for stable and captures all the eigenvectors. It's the span of all the eigenvectors with eigenvalues less than 1. And EU captures the rest. So, so what you can show is the following. You can show that locally there is a disk, okay, that the way that behaves your dynamical system inside that disk is essentially the same as if it was a linear function, as if it was a linear dynamical system. This is what basically this theorem says. And basically what is really important for you to know is that now, you know, if you at this critical point 0, if you converge to that point and you are always at that ball around that point, it means that you lie in a low dimensional space, which is called WCS, which stands for, basically this is a manifold that stands for center stable manifold. So in a nutshell, what it says is that in a small neighborhood around 0, if your function is a diffeomorphism, then it looks like linear dynamical system. And this means that if you converge to 0, you should lie on a manifold of dimension the same as ES. So this manifold has dimension the same as the number of eigenvalues, the number of eigenvalues that have absolute value less than 1. So if this the dimension of this manifold is not the full space, so if the dimension of this manifold is less than, let's say, n is the whole dimension, is less than n, it means that it lies in a lower dimensional space. Now, it's not a linear space, as it was for the quadratic case, but it is a manifold. It's a low dimensional manifold. So I hope, I mean, it's rather technical, this theorem. If you want to remember something, it should be, there is this stable manifold theorem, and that it essentially tells you that you can linearize your system, and it's a very important fundamental theorem in dynamical systems. So now, how to prove our result for gradient descent? Basically, you need to compute the Hessian of gradient descent. So the Hessian, you need to compute the Jacobian of the update rule of gradient descent. And the Jacobian of gradient descent is not, as we said, is identity minus step size times the Hessian of your function f. Now, if you choose your step size to be 1 over L, you are guaranteed that this matrix has all its eigenvalues in the 0, 1 open interval, which means that this matrix is always invertible. I mean, you can see that if the step size is 0, this gives you identity, which is always invertible, right? So for small enough alpha, this matrix should be invertible. And the invertibility is a sufficient condition so that you have diffeomorphism. So in particular, as I told you, the update rule of gradient descent satisfies the properties of this stable manifold theorem. So what you can say is the following: if 0 is a strict saddle point, this means that the Hessian has a negative eigenvalue. Now, since the Hessian has a negative eigenvalue, you are guaranteed that this matrix has an eigenvalue that is greater than 1. Okay, so if all the eigenvalues of the Hessian are positive, then you are guaranteed that the eigenvalues of this matrix are in the 0, 1 open interval, as I told you. But basically what I needed was that all the eigenvalues of this matrix are positive, not in the open 0, 1 interval. I just wanted the positive to have invertibility and hence diffeomorphism. So if you have now a negative eigenvalue, this gives you 1 plus 1 minus a minus number. So it gives you a number that is greater than 1. So in particular, this matrix will have an eigenvalue that is greater than 1, which means that in the previous theorem, where you do the decomposition of your space to ES and EU, ES is a vector space that has dimension less than n. Okay, so it's lower dimensional. It's lower dimensional than Rn. So this says that also the manifold, because we said that the manifold has the same dimension as ES, this has also dimension less than n. So basically, intuitively, you can think that if you have a set, a manifold that is lower dimensional, it should be a measure 0 set. Okay, so basically that's the whole thing. So what you can show is that all the initializations, so that you converge to 0, to the critical point 0, to the strict saddle 0, it's a union of measure 0 sets. So basically, I don't want to get into the details, but it's essentially a union of the preimages of that lower dimensional manifold. And the preimages with respect to the update rule of gradient descent. And we said that so the preimages, basically, because it's a diffeomorphism, the preimage of a measure 0 set is also measure 0. Basically, it means that all the initializations so that gradient descent converges to 0 is essentially a union of a countable union of measure 0 sets. So basically, it's a measure 0 set that was the key point. Okay, and so you can show that the set of initializations so that gradient descent converges to 0 have measure 0. So if you take any continuous distribution in Rn, the probability to, if you sample a point from that distribution, the probability to start from a measure 0 set, basically it's 0. So in a nutshell, what we did was show that gradient descent avoids strict saddle points, and this was just an application of a very well-known theorem from dynamical systems. So with this, I finished the technical part about gradient descent. If you have any questions, please ask me before I go to more technical stuff, to other technical stuff. Yes?
I have a question. Could you go back one slide?
Yeah.
Yeah, this one. So what's the reasoning why EU has dimension greater than 1 again?
So EU has dimension at least 1. So
yeah.
So ES and EU, okay, the sum of the dimensions of the two sets is n.
Yeah.
Okay, so S is the number of all the eigenvalues that are less than 1, and U is those that have greater than 1.
Right.
So if it is a strict saddle, if 0 is a strict saddle, it means that the Hessian has a negative eigenvalue.
Right.
So if it has a negative eigenvalue, it's easy to see that identity minus step size times the Hessian will have an eigenvalue that is greater than 1.
Oh, I see.
Because identity gives you,
yeah,
when you have identity, you shift by 1.
Yeah, I see.
So it's 1 plus a positive, 1 plus a positive.
I see. Thank you.
So you are guaranteed that EU is at least 1 or ES is less than n, is at most n minus 1.
Right. Got it. Thank you.
So the manifold, yeah, is lower dimensional.
Right.
So, right. So
I have a question. Can I ask you?
Yes.
So this is a Jean-Louis share. So so I wonder how this results here translate to a stochastic gradient descent. So in that case, so they're not exactly the same. The setup point from
right. So I'll tell you. So yeah, it's a very good question. So when you have so think that now what I'm doing is that I add the noise in the beginning, and then it's deterministic. It's completely deterministic. So when you have stochastic gradient descent, every iterate is it's the gradient plus noise. It's a random variable, right? That in expectation gives you the gradient. So all these results basically. So there are two kinds of results. There are those that have just asymptotic analysis, and there are the results that they have rates of convergence. So results about SGD, basically there is a paper in 2020 that shows that SGD also avoids saddle points. So the stochastic version also avoids saddle points, almost surely. And there are also results since 2015 by Ronge, and then there were some results from 2017 that show that you can reach after, let's say, the Lipschitz over epsilon iterations, you can reach an epsilon point that you know, it's far from being strict saddle. Basically, so you can in finite time you cannot guarantee. Basically, in polynomial time you cannot guarantee to reach a point that is a local minimum. Okay, so to define to say that you avoid strict saddles, you need to quantify how much it is a strict saddle. So there is this definition where you say if I'm smaller than minus epsilon, where epsilon is a positive constant, okay? If the minimum eigenvalue is less than minus epsilon, okay, then this is called an approximate an epsilon approximate strict saddle, and there are results that say that you know, in Lipschitz over epsilon time, you avoid basically you avoid these points. So you converge to something that is not strict saddle according to that definition. But you might converge to something that the minimum eigenvalue is still negative, okay? But it will be very, very close to zero. So for asymptotic results, we know that SGD avoids strict saddles. But if you want rates, you know, you need to quantify the strict saddle. So how much negative is the minimum eigenvalue of the Hessian? And according to that number, you can have some rates. Yeah. So all you know, these results that I just mentioned had uses constant step sizes. Okay, and this is very crucial for the analysis because what I told you about linear dynamical systems was about homogeneous, right? So what happens, let's say, when you have linear dynamical systems where your matrix changes with time? In this case, there are some results, but not a lot, and you need to have a lot of assumptions. So basically, but we can show that gradient descent avoids saddle points even if the step size changes with time, as long as and it might be vanishing. So the step size might go to 0 as k goes to infinity, but as long as is of at least order 1 over k. So it cannot be very, very small. It cannot shrink with, let's say, exponentially fast, because in this case, gradient descent will get stuck in something that is not even a critical point. Okay, so you need your step size to be small, but not too small. So at least of order 1 over k, and at most constant. So in particular, what you really want is that the sum of the step size, sum over k of alpha k, this is a divergent sequence. Okay, so that's, so yeah, so results go through even when the step size changes with time. But everything I have told you so far is about unconstrained optimization. So the question is, what happens in the constrained case? So unfortunately, in the constraint case, what you do is you do gradient descent and then you project. You do gradient descent and then you project. This is called projected gradient descent. And unfortunately, projected gradient descent does not avoid saddle points. And this is a bit counterintuitive. But, I'll give you an example for that. But, if this is the case, necessarily the critical point should be on the boundary, because if it is in the interior of the constraint set, then you should avoid it, okay, because of the previous machinery. So when you have constraint optimization, the problem happens whenever the critical points are on the boundary. So keep that in mind. It's important in general. So here is an example. This is a paper from 2019. So basically you have this function here, okay? And you have just one constraint that x plus y is at most 0, just one linear constraint, okay? This function might seem a bit, complicated, but you can have even easier versions of it. So two variables, x and y, plus one constraint, x plus y at most 0. So 0, 0 is a critical point. You can show that the Hessian of this function has negative eigenvalues. And moreover, you can show that the eigenvectors, it's not that the eigenvectors point outside the constraint set. They also point inside. So this is a strict saddle, not only in the unconstrained case, it is a strict saddle under the KKT conditions, okay? So it is a critical point, it satisfies the KKT conditions, and it has an eigenvalue that is negative that points in the set. So what you can show is that, so if this is the 0, 0, the critical point, you can show that if you start anywhere from this rectangle, you start anywhere from this rectangle, you square, basically this small red square, you converge to 0, 0. And this red square has positive measure, of course. So there is this interesting difference between constrained and non-constrained optimization. In constrained case, projected gradient descent does not necessarily avoid saddle points, even in the innocuous case of linear constraints, okay, linear inequalities. So this is the motivation for the last part of the talk. And the last part of the talk is about basically a particular framework where you have simplex constraints. And then we will see an application for non-negative matrix factorization. So suppose that I'm interested in this particular optimization problem, constraint, where the constraints are basically, the constraint set is the simplex. So the simplex, I have this definition on the top right part of the slide. So positive orthant intersection with the sum of all coordinates equal to 1. So as I told you, unfortunately, even for these cases, projected gradient descent does not necessarily avoid saddle points. So, so the trick here is to use another first order method. Basically, for those that have worked in algorithm game theory or online learning, you are familiar with this algorithm, multiplicative weights update algorithm. So the definition of multiplicative weights update algorithm is this one. So basically, the next iterate is equal to basically the current iterate times 1 plus the step size times the gradient, the partial derivative at the ith coordinate, and then you divide by the renormalization term. So the denominator is the same basically for all the coordinates. Okay. So what is this algorithm basically doing? Well, basically it has projection for free. So what does this mean? So if your initialization is a vector that is non-negative, okay, as long as the step size is small enough, you are guaranteed that the numerator and the denominator are both positive. So if the current iterate is positive, then the next iterate is positive. Moreover, if you sum over all the iterates at time t plus 1, basically, because this is a renormalization term, it turns out that the sum of the coordinates is equal to 1. So if you start from a point in the simplex, multiplicative weights update maps you to a point in the simplex. So you don't need to do projection as you might have to do with projected gradient descent. So, you know, you do a gradient step, then you might go outside the simplex and then you have to project back. Here you have the projection for free. So, moreover, let me tell you that simplex is, you know, it's more like the canonical form, but any polytope you can do affine transformations and transform it to simplex. So we have this theorem here that says the following. So suppose that you have a function f that is twice differentiable, continuously differentiable in a set that contains a simplex. As long as you can choose the step size small enough, then you are guaranteed that you will avoid the strict saddle points. So strict saddle points now, because we are in the constraint case, basically are stationary points that satisfy the second order KKT conditions. Okay. And the KKT conditions are the conditions with respect to the simplex. So in particular, if we run multiplicative weights update for the previous problem that these guys had, as long as we add an extra constraint, let's say that the sum of x plus y is at most, I don't know, -1, for example. So between 0 and -1, then you are guaranteed that the multiplicative weights update avoids strict saddles. So what is problematic here is that you need to have a simplex. Okay. So if you have constraints that are more complicated, we don't know if this algorithm has any guarantees. Moreover, this theorem talks about avoiding strict saddles. So we can also show convergence to second order stationarity whenever f is a polynomial function. So if f has the assumption that is a polynomial, then we can guarantee that multiplicative weights are not only avoids all these strict saddles, but also converges to stationary points that are satisfy the second order KKT conditions. So that's an interesting thing that multiplicative weights has that projected gradient descent doesn't have. It's not only that you have projection for free in the simplex, but also you are guaranteed to avoid strict saddles. So, and let me conclude my talk by giving you an application to non-negative matrix factorization. I think non-negative matrix factorization needs no introduction. It has a lot of applications in computer vision and so on and so forth. So you are given a matrix V, non-negative, of size n times m. And you are also given a positive integer r. And what you want to do is basically decompose V as a product of W times H, where both W and H are non-negative. And typically R is much smaller than N and M, okay? Think, for example, the problem with dictionaries. So here you have the optimization version of NMF, where basically you don't want to decompose V as W times H, but you want to minimize the difference between V and WH. And we consider the Frobenius norm, okay? So we want to compute W and H in the positive orthant. So the entries of W and the entries of H are non-negative, such that V minus WH is minimized, the Frobenius norm. So let me just tell you that one of the most celebrated algorithms for this problem, practical algorithm, is the Lee-Seng algorithm from 2001. So what it does is that the matrix W at the iterate t plus 1 is the matrix W at iterate t. So this circle here means entry-wise product, and the ratio here means entry-wise division. So entry-wise, you multiply WT by the matrix V times HT transpose, and then you divide entry-wise with this one. Observe the subscripts. So to compute WT plus 1, you use WT and HT, but to compute HT plus 1, you use HT and WT plus 1. Okay, so basically, this algorithm is not concurrent in the sense that you don't have concurrent updates for W and H. First, you update W, and then you update the matrix H. It is called alternating minimization, basically. So this algorithm guarantees only convergence to stationary points. NMF typically is NP-hard, the decision version. Decision version, I mean, you know, the minimum is 0 or is not 0. So it means V can be written exactly as W times H. So this is the decision version. And even this problem is NP-hard. So the tricky part is that the positive orthant, the constrained set is unbounded, and then the gradient of the function is not Lipschitz. And moreover, you have something that is called continuum of critical points. So if W comma H is a critical point, and consider D to be any non-negative invertible matrix, for example, take a diagonal matrix with diagonal entries positive, then W times D and D inverse times H is also another critical point. So you understand that you can have a continuum up to rescaling. So you multiply W by 5 and you divide H by 5, it gives you the same solution, okay? So this creates a continuum of critical points. And this is very, very challenging. So how can we do it tractably this? So the idea is to add a linear constraint, basically. And we define what we call the simplex NMF, where we add the extra constraint that the sum of the entries of W and the sum of the entries of H should be some constant C, where this constant is chosen to be 2 times, depends basically on the dimension of V, on the Frobenius norm of V, and on the positive integer R, the intermediate dimension. And what we can show is that basically SNMF is equivalent with NMF. So every critical point of NMF has an equivalent transformation point of SNMF, basically, and any second order stationary point of SNMF is also a second order stationary point of the original NMF. So under this theorem, what essentially you say is that, okay, I will run multiplicative weights, update on this function f by rescaling all the matrix by this constant C, and then multiplicative weights is guaranteed to converge to a second order stationary point of SNMF, but this point is also a second order stationary point of the original. So we have an algorithm basically that asymptotically is guaranteed to give you a second order stationary point for non-negative matrix factorization, a question that was basically open because the best we knew was the least rank algorithm that converges to stationary points. And by that, I will end my talk. Let me just tell you that, I talked about basically non-convex optimization, okay? Gradient descent that avoids strict saddles. Unfortunately, project gradient descent does not. So if you have linear constraints, why don't you use multiplicative weights update? There are other algorithms as well that you can use. Basically, the last couple of years, there have been a lot of results. So if you want to do non-negative matrix factorization, you can add an extra constraint and things will get easier. And some questions for the future, first order optimization methods are preferable because they are easy to implement, they are fast, but we might have to go beyond first order methods. Then one question is, okay, project gradient descent does not work in general. Under can we characterize the settings where project gradient descent works in constraining optimization? Because project gradient descent is what people will use if they have no clue about the landscapes. And then one thing that I'm really interested in, and people are working a lot actively, is to go one level up and instead of minimization, check about min-max optimization. And these are settings where are used a lot in general in training of GANs, generative adversarial networks, and people are working a lot on designing methods that perform well for min-max objectives, when the objectives go beyond non-convex, non-concave. So with this, thank you so much for your attention.
Okay, thank you, Ioannis. Are there any other questions that people have? We had a few during the talk.
I tried to do it in 1 hour. Hopefully I wasn't out of time.
Just slightly over. I had one other question. So there was a question earlier about the stochastic gradient, the sort of stochastic optimization, and then another way in which a lot of the practical loss functions that people look at differ a little from the theory assumptions is smoothness or differentiability, right? So there's a lot of deep network models that use something like these rectified linear unit nonlinearities that have a non-negative point, or hinge loss is very popular, and people do, I guess it's a gradient descent to optimize these things. So what's your sense? Does that just give technical problems, or does that actually change what the result is?
Definitely things are getting harder when you have, reloose and your functions are non-smooth. But there are some techniques that are called smoothening techniques that basically people are. I mean, I have seen some results where basically they are trying to do smoothening and optimize the functions. But in general, yeah, I mean, when you want to do training, zero guarantees. Yeah, I mean, we don't know.
So the smoothing, you construct a smooth function that's close to the original one.
Yes,
and
yes, you try to approximate. Right, right.
And show that they would have similar behavior. Is that the essential idea?
Yes, yes.
Okay.
And then I have a question. So could you just talk a little bit about the state of the art in min-max optimization?
Right. So first of all, okay, let me tell you that when your function is not convex concave, so which happens in GANs all the time, right? You are not guaranteed to have an equilibrium. So when I do minimization, I'm always guaranteed to have a local minimum, right? But if you have min-max, you are not guaranteed to have an equilibrium. So there has been a lot of work about what is a good solution concept. So people have defined notions like local NAS. So you want to have a point that is locally, what is a local NAS? It means that if you fix, so suppose you have two variables, two vectors, x and y, and you are at a critical point x star comma y star, if you fix x star, y star, and you perturb y, then your function will not decrease. And if you fix y and you perturb x, then your function will not increase. If you are max min, okay, max for x and min for y. So there are also other notions. And so the state of the art. So most of the results are about convex concave settings. So people are, so as I told you, we care about training GANs. So people care about convergence in the last iterate sense. So meaning that we really want the trajectory to converge to a point, and we don't want to do averaging or other stuff. So there are some people are working on this stuff, which are called last iterate convergence stuff, but all the results are about convex concave. So now for non-convex, non-concave, the only results that I know are about the local behavior. So there are also results that say, all these results are recent about the complexity of computing, this local NAS. So this is as hard as computing a NAS in real games, in normal form games, two-player normal form games, PPAD complete. Yeah, typically people, we don't know much. that's the answer. I mean, yeah, most of the stuff we know are about convex concave settings. So it's yeah, it's a big area. We are still I mean, as I told you, the motivation is the GANs. So we are still struggling because min-max is not equal to max-min. There is no min-max theorem. The von Neumann min-max theorem doesn't hold. So it's not even clear what the correct solution concept should be. So not many stuff are there. Yeah.
Okay. Well, thank you.
I tried to cover, 2-3 papers that I really know about different directions, but still it seems that it's just 2-3 years people are exploring. I mean, yeah.
All right.
Yeah,
Well, we
yes.
are over time, so I think we should
Okay.
wrap up there. But thank you for a very interesting talk.
Yeah, thanks for